So today we have a Associated Research Incorporated dielectric tester slash Hipot Tester. This came out of the garbage can at work. I was very surprised. Backside has basically the same connectors on the front as well as a it looks like an installable RS-232 module and signal input and output things. And then you can see there's obviously a fan in there because there's air vents and some relatively large heat sinks. Most thing I've noted is this thing is incredibly heavy. It weighs like 15 or 20 pounds, considering it's like a half U unit. I don't know why the hell it's so heavy. Well, actually that's not true. I can know exactly why it's so heavy. It's because there's an enormous transformer in it. So I have powered it up, and it kind of works. Let's go through what the behavior I'm seeing is. Normal IEC power cord. And if I power it on, you can see it. That is not a healthy display. So, buttons all do something. If I hit test, it obviously is attempting to say interlock is open, but it looks like the LCD is failing itself. So I would assume that this was probably disposed of because the display pooped itself, which means there's a really good chance it may actually work. So I'd also be curious to try, because it has a serial interface, which makes me think you might be able to run this remotely. So the fact that the display doesn't work might not even really be a problem. But I'm going to see if I want to take the side off and see if it's like an off-the-shelf character-based LCD, in which case I may be able to just buy a replacement LCD. That is very... These screws are very tight and have very low quality metal. Yeah, anyways, looking at the bottom, you can see here from this very large bolt that there's obviously a toroidal transformer right here. And then we have attachment fittings. So I think I might have just munged up some of these screws a bit. So there are all the screws, so let's see what we have. Okay, slides back and lifts up. Wow. Okay, it has two transformers. Wow. There's a bunch of shit in here. So we have... wow, look, there's a ferrite on the ribbon cable. That's pretty unusual. So we have... Okay. So this is a very, very unusual transformer. So it appears we have a toroidal transformer, presumably just for normal power, and then we have this very unusual high voltage output transformer. So if we actually look down here, we can see there's, cable running through a piece of sleeving, transparent plastic sleeving. So this is obviously like a high voltage output, and you can see this entire thing is like resin potted. So, yeah, you see you have a number of leads going to the center area right here, and then two leads coming out of kind of the perimeter. So I would imagine, these two are your high voltage output leads effectively. But that is very interesting. So I would assume that this transformer runs basically the normal course of everything, and then this is turned on and off for the high voltage testing. So, ribbon cable. Okay, that's nice. It's keyed and everything. So we have a lot of discrete logic over here and various parts. Here's obviously a Dallas battery-backed RAM thingy. Two PLCC packages, 3 PLCC packages, here's one as well. But if we look underneath that, we have another board which appears to be mostly the analog and possibly common mode stuff. Looking at the back, you can see we have heat sink with a fan on it, and then I see two what is it, TO253, two big power devices on this side, and there's probably two big power devices on this side, which makes me imagine they're probably using an H-bridge to drive this transformer. So I bet they're driving this as an inverter rather than directly. Other stuff that's interesting back here, here's a big toroid in line with a bunch of the transformer leads from the look of it. Yeah, so they come here and then they all go through this toroid and then come back down here. So I wonder if this is for common mode filtering or something. It's a little just, the fact that it's just kind of dangling here is kind of how you doing. Oh yeah, and you can also see this lead here, which again also goes through a tube and runs over here, is connected to the high voltage output on the rear. So they have something labeled cont check and return. I would assume that there's like interlocks. A lot of this stuff is very safety everything, because they're putting out a lot of high voltage here. This is, probably does 5 kilovolts at minimum. This thing there's 3 boards stacked up back here. It looks like the serial module connects with a cable. Oh wow, there's very fancy buttons on the front too. This is an impressive bit of engineering. So actually, oh, this is quite interesting. So here's our high voltage board, correction, there's 2 high voltage boards here. This is actually really interesting. So we have one primary, this ribbon cable here goes down to this board here, and we have a bunch of relays and various 8-pin devices. And then there's this cable which goes through another ferrite, my, which then runs to this section here, and this little strip here is another circuit board. There's actually a split right in this line right here. So our power comes in, or at least I hypothesize it's the power, and it runs to this circuit board. And then we have these, which I think these are high voltage relays. So it appears the front and the rear high voltage connectors are actually just ganged in parallel, which is kind of surprising. That implies the high voltage relays are probably more of a safety thing. Let's see if I can get a multimeter in here far enough to test. Yes, so just the 2 high voltage outputs are not independent or switched with these relays, which is a little interesting. But so we have lead comes in, we have what I think is a high voltage relay, but I also see down here there's a high voltage diode right here. I don't know what all this is for. Actually, another thing I'm noticing right now is we only have 2 wires from the transformer running to this board. So I wonder. Oh yeah, that's also interesting. You see, there's optos here. Well, how is this board powered? Oh, and then. So I think a lot of the logic's actually on the rear board, because you can see these 2 brown leads here, which. Oh no, wait, never mind, they run to this board. So those are the safety leads, which, oh, they also run to the back, so I think those are probably also in parallel. Let me check that. So, cont check, yep, those are in parallel, and return are also in parallel. So it appears it's just 2 outputs with nothing particularly special about it. So what I am seeing, though, is the LCD, which appears to be kind of barfing, is in fact just a common LCD, which is nice. It means I can probably replace it. Yeah, so both of these leads here are the cont check, and there's just 2 of them. So this is obviously our high voltage divider for sensing the output voltage, and it also looks like there's only 2 leads here, so that's a just a series inductor. And then this, I guess, is current limiting, 2K. So that it looks like there's 4K in series, so that's basically going to limit your maximum thing to, what is it? This, I guess, is your high voltage capacitor, and then that would basically say that at 5 kilovolts you're going to pull a little more than an amp if you short it at most. I also imagine this means the fact that, right, I have to cut these zip ties off. The fact that they only have one high voltage diode means they're only halfway rectifying this. So we have these really quite extraordinary toggle buttons for the front, which I think these are lights on the rear of them, and then the power switch is further down below, which appears to have cables that then run under here, and I see them coming out here. So it wouldn't surprise me. I think that, yeah, so those appear to then run over to this connector here, which is, so this is the mains input board right here. So I think those are switching the mains, which is a little how you're doing when you then realize that they're just bare here. They don't have heat shrink over them or anything. But then I suppose if you just look over on the other side of the board, there's, you know, who the hell knows how much voltage on this bare terminal here. So I guess they're like gave up on trying to protect things. So what I'm curious about is all these relays. You can also see there's an enormous slot in this board, because where is the power for these relays coming from? Considering there's opto-isolators right here specifically. Let's see if I can, there it goes. So here is our high voltage board. So first of all, the first thing I'm noticing is this appears to be conformally coded. I believe this is a resistor. I don't know why it's in a piece of fiberglass tube. But yeah, so you can obviously see... Okay, now I'm really confused. So, looking at this board, we have what I assumed was isolation right here. Obviously these are 2 Fairchild 4N33 opto-isolators. You can always tell an opto-isolator. You basically only ever see white packages like this are pretty much exclusively used for opto-isolators because white reflects the internal LEDs more efficiently. You know, so they have a, they obviously have a little bit of clear plastic or some sort of clear material in there, and then they pot over it. And if you pot over it with black, you only get the direct path, and if you pot over it with white, you get reflections off all the walls, so your current transfer ratio goes up. But I think that, I don't know, it's probably not as linear or who knows what. So these, you look at something and it's white and it's like, oh, that's an opto. But if I look on the other side of the board, they're not using them for isolation. I don't know what they're using them for. But you can obviously see each one of these giant blue boxes has 2 terminals, which would pretty much tell me they're relays. I think a lot of high voltage stuff like this is switched with basically read relays. So, come in, we go through this diode to... Okay, I think this is, so it looks like one of the... Come in, so the diode runs to here, and then we have another... So it runs through the diode through a 1K resistor to this terminal. And then there's also a 5K resistor back to this terminal, which is, so this is our output right here actually, because that's where it goes over to the other board. And then we also have this option here, which then switches between these 2 terminals, and then it looks like I don't see exactly where that trace runs, but I would assume what they can do is they can switch in and out this capacitor. So I would assume that that means if they jumper the high voltage diode, if they jumper across the high voltage diode, they just have the direct path to the output, so they can output AC. And if they don't jump across the high voltage diode, they open this relay and close this relay, you get DC output. So I don't know why they need to go both directions like that, but I guess they felt the need. So that would be what all this is. So this is like a configurable AC-DC output that it's not going to produce very much in the way of any current, but with Hipot stuff, if you're drawing any current, something has gone wrong. So the reason for this physical slot this whole length of the board is because the coils of these two relays presumably operate at a much lower voltage, whatever the, all the electronics are here, and the electronics, not after, on the other side of this resistor divider aren't at high voltage potential. So they cut this isolation slot to give them much better isolation between this mounting terminal, which is again going to be connected to earth, and everything else. This lower board, they're using narrow spade terminals, which is interesting, and also just feeling this wire, I can tell there's not a lot of conductor in there, which is again in line with what you would expect given this is high voltage, low current. Oh, that's interesting. So this is, now we're looking at stuff that's good system design. They used, you can't see it. So now we're at the point where it's like, oh, this is really impressive. The input and the output spades are different sizes, so you can't hook them up wrong. That's really clever. That's the sort of thing where, and you can actually see that these are obviously getting together because they're using one of these spade terminals with another spade terminal on it. This crimp terminal actually then connects to the other one. So there's only one spade terminal on the actual circuit board for the output. So again, we have plastic standoffs for the high voltage area. I'm going to call this the high voltage sensing board because I don't know what it actually is. You can see power comes in here, goes through this resistor, and then return through this resistor. I don't know if you can make out the traces. Hold on, let me get a flashlight. Power comes in, goes through here, through this resistor to this choke, through the choke, out, and then alternatively the resistor divider then goes through here, all the way down the chain. You can see the junction between each one until finally it reaches this point, and then it runs down into the electronics assembly. So you can actually see here's the end of the divider. Comes along over here. This is interesting. They have like a shielding thing. I wonder if that's to prevent creepage across the circuit board. Down here to that point, which is just somewhere in these resistors here. Looks like there's another option for a MOV right there. So another thing I'm noticing is, so these two pins are connected together and these two pins are connected together, so that would actually make sense with this weird wiring harness. Oh, that's horrible. So I was so confused about these. It's black and red, or black and brown, black and brown. But if I follow black to the front panel connector, it's the cont check, and if I follow black to the rear panel connector, it's return, whereas cont check is brown. So the pin functions between the two panels are swapped with regard to color, which is why this is black, brown, black, brown. That's pretty shitty. But yeah, anyways, it looks like, I would assume a lot of this is like range switching for the analog front end. Non-populated TVS, these are labeled ZP. Oh no, we have a bunch of TVSs. These are all spike suppression stuff. I bet a lot of this is to handle all the weird shit that happens. So if you're Hipot testing something and you get an arc, suddenly you go from zero current to lots of current, and things can ring and do all sorts of really interesting things. So I bet a lot of this protection, all these MOVs, are to deal with all the fancy crap that happens when you get a really big current spike and then your output lines ring and you have all these long test leads running to your equipment. So this is probably like pretty much extensive protection of the inputs. And then a bunch of relays to switch resistors in your front end. This is a TLO84. That's a really generic jelly bean op amp. It's actually kind of amusing they use those. I guess it's good enough for what they needed. But that's like an old classic op amp. Actually, looking closer, some of these other parts are a little more interesting. TLO84. That's an OP07. That's a fancier op amp. That is an intersil part. I can't quite make out the CA315 LOC40EZ. And this is a, I don't know who makes that, Claire, LOC111. It's also interesting, all of these are socketed, so presumably this is intended to be repairable to some extent. And then this single TO220 device is obscured by a capacitor, but that is an 7805, so that's just a voltage regulator. Other things you can see here, we have one transistor. So I assume either one of these devices is acting as a relay driver, or they're probably running the relay coils through to the connector. Looking on the bottom, I can actually see one of the relay terminals for all three of them is ganged together, and then the other one is on the far side, and I don't know where it goes. But yeah, so this is just typical kind of analog signal processing type stuff. We have a couple film caps and miscellaneous bits and bobs. So they like, we have black and brown, black and brown, black and brown. So this connector here is labeled low. So I'm wondering, this I would have assumed is power coming in from somewhere, but it's also possible that this is DC voltage from things. Oh, I actually just noticed, so coming out again with too many zip ties. So you can actually see we have a lead coming out of the transformer and going directed to earth. So I wonder if there's shields inside the transformer. That wouldn't surprise me. That's a little esoteric. Oh look, here's even more black and brown leads. Goodness gracious. Yeah, so then this is tied directly to an earth post, and then I also see another one. Actually, yeah, so it appears this lead that's also tied to that earth post runs to the, there's a threaded earth fitting on the rear. Because again, all sorts of weird crap happens when you have really, really big sharp edges at extremely high voltages. You can also see that our rear panel here has a relay on it and a bunch of other junk. Some series resistors. There's a line switch back here. But it looks like, so looking at this, I'm seeing we have these red and black leads which then run down to the front panel on the front of the unit. So, but nothing else is heavy, so it looks like these the four leads that go through this big choke here are, I would assume, the 120 volt input to the transformer. I don't know why there's additional, these two black and brown leads that run down to the lower board, because I would have assumed that this wouldn't be mains connected. Sorry, I got distracted. It's really ironic because one of the projects I'm working on at work, we really need a Hipot tester. And then I'm rummaging around in the trash today and this shows up, so I'm a little excited. I really hope I can fix this. This is really so Mickey Mouse. Anyways, looking in here, you can see we have just a generic WinStar LCD module with a ribbon edge connector on it, and then buttons, which then connect through this 12-pin ribbon cable. So that runs all of this stuff. It also appears there's an LED behind this lightning, the lightning indicator, which is cute. And then you have these, the green is recessed into the front panel and the red is proud of it, which is kind of cute. And those are relatively fancy switches. Feel very nice and everything. So I'm going to leave that. Well, I really wish that could be disconnected. Looking back here, they just zip tied everything to everything. So obviously, again, here's our power switch leads. That was exciting. power switch leads just run over to here. Bare spade terminals. And then we have input filtering, and it looks like input fuse and etc. And then we have all of the browned leads. I wonder if there's like a sale on brown wire or something, because good golly. Oh, okay, so this is interesting. So these two leads actually run to the transformer. One of these is the what I think is the other terminal of the high voltage output, and one of them runs to the interior winding. So now I'm curious. I can't untangle my multimeter leads from the mess that is my workbench. So one should be here, and one should be, I'm guessing it's between this and this. So it looks like our secondary is 11.7 kilo ohms. So that was between this brown lead, which is actually labeled with an L on the side of the transformer, I can see, and I actually also on the board it says here low. And between the this high voltage lead, which is labeled I/P. This is actually also labeled I/P. Oh, and this is labeled H.V, so this is your high voltage output. That's cute. And then this is con and ret. So, you know, obviously connection and return. So, moving on, let's see if I can't take the back plate off as well. So the only thing remaining now is the earth lead and the serial module, which I should be able to unplug. Though I may have to clean up, again, what appears to be very hardened silastic. So here's our serial interface board. So this is about what I expected. There's not much here. We have a Max 232, which is just a level translator for serial. And then it appears we have two optos. That is a 6N137. That's also a 6N137, 180 degrees rotated. So I'd assume this is like DTR CTS type stuff. This is another 7805, so presumably whatever the host carrier voltage is, it's higher. This on here says RS232-1 Yahoo, presumably somebody's name, 2006.11.15. So that's interesting. This is a relatively, I mean, it's after the turn of the century, which means this is probably through hole for, I don't know, maybe it's a legacy design or something. Here is our power board. We can see these very, very nice little brass right angle adapters to mount the board to the rear plate. Here's our power input. We have MOVs between each input and the chassis, which is kind of a neat touch. So you can see this MOV is hiding it, but one terminal runs over to this pin here and the other one runs to... Okay, so power comes in, it runs to the fuse, which is these two terminals, and then I would assume, yeah, it comes from the other side of the fuse and runs to this, which is our power switch. And then from the power switch, it runs through these two big power resistors, which are each 5 ohms. And then it runs over to the power output connector, which is what this, oops, so, sorry. It runs over to the power output connector, which is what these are. Looking in here, okay, so we have this relay, and this relay, okay, so this pin, these two pins that come up from the lower board just run the coil on this relay. And I would put money on it that that relay just shorts across the two input series resistors. So I think what this is this is a soft start mechanism, where you turn it on and then once the capacitors or whatever internally have charged up, this relay then shorts across these, so that shorts across the 10 ohm series input resistance. So that's all that is there, is it's just a fancy soft start system. So looking at this board down on the bottom here, we have what appears to be even more relays. I'm seeing a label over here. This is labeled AMP3670. So, okay, and then considering I see resistors next, big power resistors, which are 5 watt 0.1 R. So this looks like this may actually be like an analog amplifier. And these are current sharing resistors on power transistors. Because unlike FETs, BJTs have a negative temperature coefficient. So in other words, to get them to share current properly, you have to have very small resistors in series with all of them. And then there's also a temperature sensor, or a temperature probe, either an overtemperature cutout or a temperature probe, just a general temperature sensor right there. So does it look like this board will come out easily? So we have red, black, and brown here, which are the outputs of the big toroid. And then we have black and brown here, which are inputs to the high voltage transformer. So just because I'm curious, let's see what the primary side resistance is. One ohm. Yeah, so 1 ohm and 11 kilo ohms. That's about what you'd expect for something that's doing this sort of ratio. Oh, and then we actually, so in addition to that, we have a giant pile of secondary outputs down here, which then just plug in. So it appears, you can just tell from the wire gauge that these outputs here, this is probably your primary, I bet it's a bipolar supply. So you have a center tap and then two. Actually, we can generally tell. So 0.8, 0.8, 1.3. So the reason you don't see 2x is because the multimeter probes themselves have 0.4 ohms of resistance. So we saw 0.8 would be, so we'd have 0.4, 0.4. So that would mean that we'd have a 0.8 total resistance, and then if we measure across the entire thing, we'd see 1.2 or 1.3, because that's 0.4, 0.4 plus 0.4. So yeah, so this is going to be your main output, and then this is probably a bunch of various intermediates and logic supplies and who knows what not. So what I'm getting from this so far is this is a very old school design. I mean, you've got what looks to be like a straight up, probably like a class AB output amplifier. And I guess if they're not, trying to minimize, dissipation, no reason not to. It's just, I mean, it costs more, but I bet this thing is hideously expensive new. Oop. So, I mean, you're looking at, a pretty near cost, no object design, so why not, go with something super classic and extremely well understood. Yeah, so we have, okay, this isn't, what I'm seeing is these two capacitors are in parallel, which means this probably doesn't have a bipolar supply, which means I'm not entirely certain how it works. What I'm also seeing is these two devices appear to be in parallel, and these two devices appear to be in parallel. And then you can also see that each one appears to be... So these two, one terminal of these power resistors is connected together, and then I would bet the other terminal of the power resistors... yeah, it does. So the other terminal of the power resistors goes to one of the terminals of these big power devices. What are these devices? It's a Toshiba part. Looks like C5198. This one is C5198. Let's see if the other side are the same. A traditional bipolar amp would have NPN and PNP devices. But the Toshiba etching is very difficult to read. Okay, they're all C5198s. So this could be... So what is the other terminal? So I'm looking at this, and the way the AC comes in, and our two, our center tap's in the middle, and our two winding halves goes to in each of the inputs of the bridge rectifier. The plus for the bridge rectifier goes to one side of the capacitor, the positive side of the capacitors. Actually, that's not true. I don't think it is. It looks like the plus from the capacitor, the center tap goes to the plus of the capacitors. So, oh, it is bipolar. Okay, I'm dumb. So the problem right now is this is negative on one side and this is negative on the other side. So what we have is the plus appears to go to this pin, and the negative then goes to this pin here. It would go to here. And then the center tap goes to the midpoint. Yeah, so this is a bipolar amp. So yeah, so plus should go here, and minus should then go here. So then we'd have plus and minus, well, they're 63 volt 4700 mic cap, so it's probably like 40 or 50 volts. Obviously you can see this is connected to the heatsink because the tabs of these devices are connected to the heatsink in one case. So your outputs would then be this pin on one side, and then the... well, no, it'd have to go... I wonder, does that mean one side should have... Yeah, look, one side has... actually, I'm not sure. One side should have insulation between the power devices, because then how could they do current sharing? Well, no, it would have to be the... Never mind, okay, yeah, it's the wrong side of the transistor. That's interesting. It's all the single transistor type, though. Anyways, moving on. That's all of our power stage. We have more Toshiba C5196. And then this is a Toshiba A1941. Wait, that's actually, I think it's... This is a 5198. So this may be, like, I bet some of this is the driver stage for the power amplifier. It's interesting that they're these big TO247 parts that are unheat sunk or anything. And then you can actually see we have higher power TO92 devices. You can tell because look how much longer the body is. And that is a C2235. And then on this side we have a A965. Yeah, I mean, a lot of this looks like real classic, old school audio amplifier type layout. Look further on, this is another Oppo 7, and then this is a... What are you? 1031. I think this is an opto, which would also make sense when you realize, so this is an input, I believe, and this is an output. So that would imply that these inputs and outputs, presumably these relays here drive the outputs, and the inputs go through these optos. Actually, if we look at the other side of the board, can we confirm that? I don't see a great isolation gap. So looking on the board, I don't see an isolation gap. So if these are isolated, which I suspect they are, they're not very isolated. They're just like mildly galvanically isolated. We can also see the layout on this is quite something. I see at least 3 discrete trace sizes, and then here's 4, and then here's 5. Yeah, so this is very old school. Let me see, do I see any interesting ground layouts? Not really. I was kind of hoping I'd see like a cool star ground layout or something like that. Other thing of note, yeah, so obviously here's our power in, and then we have various diodes, and so this is a 7815 and a 7915, so presumably we have 78 and 7915. Here's a really old school circular bridge rectifier. That's pretty classy. Some assorted jumpers. I bet that's a 7805 on this heatsink. It's labeled IC, I can't read it. But I'd put money on it. That's your general purpose power supply for all the electronics. Anyways, that's an interesting little, real classic old design of, you know, basically an auto amplifier driving a transformer. But I mean, if you want to get really nice, you know, high quality, you know, high volt, you know, you want your drive signal for this to be as high quality as possible. And you don't, you know, you want something that you can guarantee will work, and you don't care about efficiency. Going old school, all analog, all like Class A/B is the way to go, because it's going to work. I mean, the design practices for that have been well understood since, what, like the 70s? I mean, earlier, and to what extent tubes are different. As trite as that sounds. What is it? Tubes are voltage gain devices and transformers are current gain devices. So the first few years, or the first 5 or so years that transistors had come onto the market, nobody really knew how to make good transistor amplifiers because they were treating them as voltage gain devices rather than current gain devices. At least that's the Apocrypha. Alright, that's now back in place. And then, alright, everything else goes somewhere else. So let's fold the rear cover back into place. Let's dangle the plug out the rear. So they're doing a lot of stuff, like for instance where they have, you know, they're switching potentially 240 volts, the center pin is not used to give them better creepage distance. Whoop. So then we just have this, which is the control signals from the front end analog board, which is this right here. Alright, so the analog board, or the digital board, is now disconnected from the front panel. And here is our bad, I need a number 1. Yep, so that's just a really common variety, garden variety. Oh, it's a 128/64 LCD. Wow, I bet I can find these on Amazon. Looks like it's got a 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20 pin interface. Hopefully I can steal this ribbon connector off here if I have to. So I'm going to plop the front panel on for the moment at least, just to keep the number of bits of junk floating around my desk down. So let's look at our probably the most interesting board of the entire assembly. Get that out of the way. So this is the control board. So big Dallas, real-time clock, possible battery-backed NVRAM type stuff. DS12C887 Plus. Bet the battery in there is not healthy at this point. This is labeled CON 3670. I didn't actually look. This is probably the 36700 device. So 74HC573. I don't know what that is off the top of my head. Here's another OP07. 74HC573. 74HC573. It looks like all these 3, 4, 5, 6, 7, 8. All these 20-pin devices are all 74HC573s. So there's 1, 2, 3, 4, 5, 6 of them, which is fairly interesting. Here's another TL084. We have just an absolute boatload of assorted passives. This has got to be a bunch of like analog magic garbage. This is an LM311. This is also an LM311. This is a 311. This is a 311. Here's another 311. OP07, 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 OP07. This is an OP. I can't read it. I think it says OP17. So this is a ULN 2003. That's a FET array. That doesn't surprise me. I bet that drives the relays. This is also an OP07. Just let me double check that. I think it's an OP07 with a different label on it. Maybe they just couldn't get all the same source parts. Correction, I believe that's an OP97. But the labeling on it's not very good. OP97F. It's an analog devices part. I can see the analog devices logo on it. Continuing. TL084, TL084. This is an HA17324. I have no idea. It's interesting. It's a different package. It's kind of a coarser package on it. Here's another one of that exact same part. HCF4051, HCF4051. LM311, OP07. This is a DAC 0800 LCN. Oh, this is also a ULN 2003. It's interesting that this one is soldered directly to the board and this one's socketed. I wonder if this is the one that switches the high voltage relays and occasionally blows out. This is an ATMEL006, ATMEL, or no, wait, correction, 93C66 and 93C66. I bet these are like EEPROMs. This socketed device here is an AD7541. I bet that's an analog to digital converter. And then we have three PLCC devices. See if I can get the sticker off cleanly. So that is a WinBond part, W78E516B40PL. One of these I would assume is the CPU. I was guessing it was this due to the proximity to the crystal, which is a 14.7456 megahertz crystal, but I don't actually know. And then up here we have, this is a SyncMOS part. It's a company I've never heard of. And I'm ruining the sticker. What will I ever do with myself now? So this is an SM8951 in the same package. And then we have this little itty bitty PLCC device down here, which also has a sticker on it. Where did I put those? So that is a lattice semiconductor GAL 16V8. So that appears to be everything on there. So one of these two devices has to be the CPU. And then we have a lot of just interfacing junk. Let's see if possibly reseating this cable fixes the graphical weirdness. There, it's just right there. So I have to be a little careful doing this. But that plugs in there. Front panel is off. Plug you in. Turn off my microscope light because it's distracting. And then, oh wow! So it was just a bad connection. Wow. So, menu, step, system, exit, menu, test, exit, menu, system, so I suspect the interlock is just the cont check to the return. So let me see if I can find something I can wedge in there. So anyways, I have to go read the documentation, but it looks like just one of these connections was bad. Go figure. So from the documentation, I have to short pins 4 and 5 on the remote signal input to enable operation. And they sell this, it comes with a thingy that does that. But fortunately I keep lots of DE9 connectors on hand and can very easily just whip something up. One interlock bypass. So, let us now. Unit is off. Power is applied. Unit is on. Let's do test. Hey, das blinken lights did das blinken lights. So turn it off. One thing I noticed is, so let's go to AC Hipot Test. Check leads. So reset. So I had done this previously, which was, I don't think that, I don't know how far in I have to shove something to get a contact. Doesn't quite fit. Some long screws. So this is very, very, do not try this at home. HV in return. Okay, so this is just checking that it sees a short. So select, open DUT connection between, turn unplug HV. Verification okay. So then if I shove my tweezers in here, okay, so alright, so reset to exit, exit. So menu, step. Oh yeah, so these are the remembered menu test. Exit, let's go to menu test. This should go up to 6 kV. So enter, ramp up, make that 5 seconds and dwell 5 seconds, or 2 seconds. Enter, ramp down, let's also make that 5 seconds. Exit. Oh, that's cool. Look at that. It's humming. I can hear it. It's interesting. I guess it doesn't go all the way down to 0. But I don't know if you heard that. It buzzes a little bit. That's cool. So now I need to come up with some things to test. So here I have a really rather unsafe high voltage lead, just a bare banana on the end of a long piece of, there's some solid copper wire in here just to give it strength. And what I can do, sorry, is YouTube on, is we can then stick high voltage across stuff and see what happens. So this is just a generic barrel connector. You can see here's the other lead, this is the return lead. And what we can do is we can now hit this with voltage and see what voltage is a barrel connector good for. So and we heard it popped at about 2.38 kilovolts. So let's see if we can see anything. I don't know if it'll visibly spark. I don't see anything visibly discharging, which is kind of a bummer. We can test other stuff. Let me see if I can find a capacitor that we can, like a high voltage Y cap. So here's a not very good switch mode power supply. I don't actually know what voltage it is because it's so cheap it's not even labeled. I think it's this one screw that holds the lid on. Wait, correction, 2. I think this came out of a really cheap 3D printer, but I have a way more of these than I really need right now, so let's see if this thing's Hipot safe. I put money on it, it's not. So I'm just taking the lid off out of curiosity. This should just slide off. There it goes. It goes the other way. Yeah, so this is a 300 watt, I believe. It actually has decent, it's got some protection circuits. This is cute. So obviously you have, these are presumably your main switching transistors with this very well aligned silpat. And then this is, I believe, your output rectifier. It is labeled DB1, yeah, diode bridge 1. And then primary IC is a 7500BD, whatever the heck that is. And it has a header for a fan that's not placed. So anyways, so our pinout here is line neutral earth output. So I will put our input voltage into line and our ground into earth, which actually I would hope, well, it may not be, that's a good point, which is I don't know if earth and out negative are connected. So they are. So, wait, correction, they aren't. What is beeping? Oh, my LCR meter. So they're not connected, which means the output's floating relative to earth. So let's start bridging to one of the output negatives. This is more crap that fell on me. So let's see what we get. So it's dissipating 4.2 microamps. So that's impressive. So let's go back into the menu. Step. Oh, there's multiple memories. Menu, test. It's 12 for 10 seconds. So you can see this is the leakage. Ha! It broke. So something. You saw the current draw increase, and something went kapoppity pop. That actually startled me. Let's see if it So can we see what is discharging? I suspect it's across the board, so let me see if I can kind of get you down there. Now I'm going to run it again. Oh, the high voltage is leaning against the camera. That makes me uncomfortable. So, alright, I think I'm safe now. Charging. Still didn't see it. Anyway, so it apparently can't handle 6 kilovolts. Let's go to the earth output, oh, that was to the output. So that must have been, presumably that was, I bet that was arcing in the transformer. Let's go to earth and see what it does. So it discharged again. So this thing, it seems, I'm actually kind of impressed. It makes it up to 5 kilovolts before it discharges. So if this was done like if somebody did a 5 kV Hipot test on this, it would probably pass, which is fairly impressive, considering how cheap it was. So I mean, if I go into menu, test, let's just turn it down to 5 kV. I think at least has some sort of acceleration. So ramping up. So it's sitting at 5 kilovolts right now. 2.7 microamps of leakage. And nothing's happening. And then now we're ramping down. So, oh wait, you know what? I'm still not on earth. I'm dumb. So, make sure we're off. Take our earth or take our negative and connect it to the earth terminal rather than one of the negative output terminals. Now let's rerun. Ramping up. Ooh, I saw it that time. It broke through the silpat. Let's see if I can replicate that. I hope the camera caught that. It's arcing around the silpat on the output stage. Or on the transformer driver. Charging. Yeah, it caught it that time. So, that's pretty cool. That also implies that if I earthed the chassis and tried to run the Hipot test from the input to the output, it would probably blow through the silpat. But I think these things are generally only rated for a couple thousand volts, so that's not too surprising. That's just cool that we can actually see it. Let's let's do it again. Or it's not doing anything. It might have blown away the... Oh, something went pop. It sat for a while. That was interesting. Let's go back up to maximum. Let's see if we can see anything interesting this time. Charging. Nope. It's still arcing around the transistor somewhere. So I bet this thing's probably not very happy right now. I think it's probably dead. Oh, that's another thing I could do. So I can go in here and we could also... So we can put it in AC mode, and this should possibly cause other interesting results, because now we'll be seeing any effect of it, like the Y caps. Or not. I believe it can only go up to 5 kilovolts AC. Enter. Let's make it dwell for a while. So, wow, that didn't take very long. Okay, so it's gone instantly now. And whatever I blew, it's now... let's go back to DC. Yeah, so whatever popped is now shorting it. You can see at 580 volts it drew 7.5 milliamps. And it's getting worse. Or it can't react that fast. Let's turn the ramp up down. Okay, yeah, so I've now pretty much irreparably damaged this garbage power supply, which I didn't care about, so no loss there, but it is interesting seeing how easy it is to basically just totally destroy one of these. So, actually, one thing I want to try keeping a habit of is shorting out the output. So, see what hold you together. I don't see any primary to secondary stuff going on, but if we look at our silpat, I don't see anything there. Oh no, wait. Oh, that's what I think it is, but it looks like there's a little burning on the top corner. I don't see anything on the back of the power device. And if I look, there's nothing visible on the aluminum shell either, aside from some really spectacularly bad machining. Looks like they just, whatever procedure they used to punch these holes out, just left a little dingus dangling there, and they're just like, yeah, we'll just tap it. I mean, I guess it was pretty stuck there, so it doesn't really matter, but eesh. Yeah. Yeah, so I don't see anything obvious. The only thing I can think of is these two capacitors. Whoops, sorry. These two capacitors are between each of the inputs to earth. You see, if you follow the trace here, they run down to the earth, which is this pin, and I was implying the voltage to that one. So I can totally see one of these capacitors failing. Oh no, wait, we weren't having the Y caps fail. We were having the it arc to ground, or it arc around the power devices. Excuse me. So now that we've removed that failure mode, what happens if we try it again? One power supply enters, no power supply leaves. So okay, so something on the board has failed because it's failing at 590 to 600 volts. So let's real quickly look at the board. So the only thing connected to earth is this Y cap to the secondary, and then these two Y caps, or these two bypass caps, across the primary. So let's remove these caps. Yep. This is pretty ridiculous at this point, but what the hell, I'm having fun. Just go anywhere. So now we can confirm if it was in fact one of those two capacitors that was causing it to immediately fail. So, connected. Yep, it was one of those two Y caps. 2 kV, 3 kV, 4 kV. Whoop. So I think we just kerpopped CY3. Let's see if I can get a better view on it. So that's the capacitor that is the only path to earth remaining. So, charging up again. I don't see anything, so it's either that or it's arcing across the actual board. Let's bowdlerize this sucker. Alright, firing again. Charging. Or ramping up, I guess would be a more accurate statement. Okay, so it popped again. So the only thing I can think of at this point is it must literally be arcing across the circuit board. So let's see if we can see it, because this is cool. So, charging. Oh, I saw a little spark right in this corner. Let's try again. Yep. So I don't know if you saw it, but there was a spark right across here, right across the insulation barrier. This is also interesting because this teaches us that this amount of creepage is good for approximately 3.7 kilovolts before it breaks down. So That is approximately I'd call that 80 thousandths. 80 thousandths of an inch of PCB. That this board isn't exactly clean, but with 80 thousandths of an inch of creepage clearance, you get a breakdown. It's also interesting because you can actually visibly tell that there's slightly less clearance here than there is, you know, in further areas, like right up here. You know, if we look at our comparative trace spacing, this is just a little hair wider. So it really does, it chooses the area where it's the shortest, smallest gap, which is right here, presumably because this is where they had to have the ground terminal, and they had to clear the, you know, the earth connection. So we just put our ground there. I've disconnected the power lead because I'm going to be honest, this thing scares me a little bit. I don't think it's really generating enough energy to hurt you. I mean, well, it would hurt, but I don't think it would, like, kill you. There we go. Yep. Same exact failure mode. What is interesting is that I'm actually connected to this pin here, so that means we must be running through here, through the common mode inductor, breaking down the bridge rectifier, possibly, and then running back through the, well, actually, I don't know, running back through all these devices and back to here. Because if we look, yeah, so it runs through here and then back in, and the fuse is here. So now that we're having fun, let's go across input to output and see what we get now. So now we're looking at the breakdown, basically the transformer. Wow, so it's sitting at 6 kilovolts. That's impressive. And dissipating 4.2 microamps. Huh. So the failing is to earth. Well, actually, that's ideal. You want it to fail to the earth rather than fail to input to output. So I wonder if they've. I mean, I guess that's more thought than it seems like they would have put into something with, you know, that's this shittily built. But it seems like it's designed so that it fails shorting the input to earth prior to failing shorting the input to the output, which was the way you'd want it to fail, because if you short the input to the earth, you're going to trip a breaker. Let's run it again. Suddenly this thing's drawing about 50, 60 watts when it's running full tilt. Oh. So it's right borderline. I bet this passes a 5 kilovolt Hipot test, but not a 6 kilovolt Hipot test. But that's cool. It's interesting how unrepeatable it seems to be. Let's look at something else. Here's a... This is just the primary... No, wait. Yeah, this is just the primary side of a power supply. I don't know why it's on my workbench. This should just go in the garbage. And so should this at this point. What else can we zap? So I just realized I didn't actually note in DC mode whether the high voltage output is positive or negative. I would assume it's positive, but, well, because what I'm realizing is I bet I can test the breakdown voltage of the transistors from that power supply I blew up with this. So okay, so this does confirm, since positive is connected to the high voltage, that it confirms that we are positive is the center pin. So what that means is I can now take the FETs off this blowed up Or I'm assuming they're FETs, I don't actually know. The power device is off this blown up power supply, and we can see what their breakdown voltage is. So, real quickly before I go further, let me just look these up. So these are, they're made by a company called Inmark. Never heard of them. 13009B. So I didn't have much luck finding, I have no idea who made these, but it looks like it's base collector emitter, which is pretty common. And there, a few of the things I found, which were for TR220 devices, admittedly, claim 700 volts. So, in any event, we can at least have a look and see what happens. So I'm going to try and video the screen while this is running. So, running the test. So it should survive this because it's a 700 volt device and it's only good up, I'm only running up to 500 volts. So yeah, it passed that. So now let's go into the menu and turn our test up to 1000 volts. So that's interesting. It corrupt at 520 volts. Let's see if it's permanently broken. Nope. So once again it fails. These appear to, whatever the other parts with the same part number I found appear to not be this. Let's idiot check, because maybe these are actually FETs and the similarly spec'd parts I found are just unrelated. So, okay, I have no idea what this is. Maybe they're BJTs. So now it made it up to 860 volts. So, whoops. Since I have no idea what's going on, I'll take one of these old open source transistor testers and have it see if it can tell me what it thinks these devices are. Thinking about it, I'm not sure if these can disambiguate between BJTs and IGBTs. I guess they probably could, because it's probably a function of the base voltage. But yeah, anyways, the battery in this thing had gotten old and now needs to be changed. Let's see what it thinks this is. NPN BCE, base collector emitter. So I was right. So not a lot of beta. So it's interesting that the base to collector breakdown was higher than the collector to emitter breakdown. I guess I don't know enough about transistors to tell you whether that's typical. Let's test the one that we may have just damaged. It didn't necessarily even damage it. I guess it's not putting very much current through it. Yeah, 626 millivolts, that's about what I'd expect. So let's go. So once again, emitter, and then collector. What happens? So once again, 1 kilovolt, 500 microamps, 10-second ramp up. So This one failed a slower voltage, and apparently the field produced by this is enough to turn on my transistor tester. I have had that happen. The reason the battery in this had gone flat was it was just setting itself off spontaneously on my bench when I didn't do anything. So if I go to base emitter, we should get no voltage. Yep, that should be, it can't show 0.6 volts, but if we go to base collector, this is the test that was higher voltage previously. Wait, no, I have them backwards, because it's just going across the diode. Yeah, see, it's spontaneously freaking out and just deciding it wants to do whatever the hell it's doing. It's not turning off properly. So, yeah, so I just had the diode in the thing wrong. So 860 volts. Let's see if I have any other interesting transistors around. So here's a little relay module. I bet this isn't good for that much voltage just because this is very Chinese. They don't have a lot of creepage distance. You can see I actually cut this one a little bit because... So basically this is a low voltage section, and actually you can see they have a completely pointless opto here. And then this is the high voltage area, but they only cut the isolation traces right to the edge of the plane. So your creepage distance from this copper point here to this trace is basically completely unaffected by the cutout, which is really dumb. If they had run the cutout, 200 thousandths further here and 200 thousandths further here, the cutout would actually be really beneficial. But as it is, it's just stupid. So normally open and COM. So I'm betting this will, I don't know what the relay internal construction looks like, but I'm guessing this will fail across the surface of the circuit board. I can get it to sit nicely. Alright, so there we are. So let's see, this thing's still wigging out. It'll just sit there and ruin its battery. So now we're testing the relay again, or the relay. So yeah, so that does a kilovolt fine, so let's go up to 5 kilovolts. Or excuse me, 6. Enter. So let's see how this thing does with 6 kilovolts. I expect it to arc right by the screw terminals. Hopefully we'll be able to see it. It may arc on the other side of the board. Okay, so I didn't see it fail, but it's possible. It short-circuited it, or it shorted at 2.09 kV, or arced. It's possible it arced under the connector, the terminal block. Let's run it again and see if we can catch anything. More critically, let's listen really carefully to see if we can hear it fail. It should make a little popping noise. Okay, I heard a little crack before it did that thing, so I think it might have actually arced inside the relay. One other test we can do, this would be perhaps more informative, is to look at what kind of isolation this entire thing provides. Another thing that I'm realizing is it could simply be arcing across to the chassis. I don't think it would, because as you can see the lid of this, it's just plastic. But let's put it on the wood of the table. Sorry, I'm trying to film with a second camera while talking, which I'm not very good at. So there's our device. I expect it to arc around in this area here. So let's .21 kilovolts before the isolation gap fails. Let's see if we can see it this time. So I don't see anything, which makes me think it's arcing on the other side, because I'm realizing that I think there's a plane on this side as well. Yeah, there is, and I didn't cut that back, so it's probably arcing from this point here, right around here, or right around here, to these corners here, which I think on the other side are like VCC, because again, this thing is really badly designed. But that's not totally discouraging. The fact that this thing handles 5 kilovolts. Actually, one thing I can do. Computer, turn off bedroom light.
Turning off bedroom light.
So now it's dark. Yeah, so it definitely arced on the other side. Let me turn up the ramp speed, or turn down, enter. So yeah, so there's a good. Oh, that's interesting. So what I actually just realized is, so this thing has some status indicators on it. And it's causing the status indicators to illuminate, which is kind of funny. One second. Alright, so now I just have some random bits of wire connected to it, but this gives me places I can attach test leads. So that goes there and this goes here. And if you look down there, that's an LED and that's an LED. That's the power LED, and that one shows when the transistor is switched. So let's rerun the test. We turn the room lights out again. So you can actually see it, it appears it starts to like corona discharge first. So actually, let's go back into the test and slow it down a lot. So now it'll take 40 seconds to ramp. So this will be real slow, and it's not going to be exciting until it gets into the several kilovolts. But from the sound of it, it was like hissing. And you saw the LEDs illuminated a little bit. Yep, see they're flickering. Yep. So it didn't do it at all when it powered it. It ran up much slower. That's interesting. Oops. Sorry, this keeps getting blown out. Oh, I know what's going on. It's because the stupid camera's gone out of focus. So, alright, now I've shown a light on it. Yeah, see the LEDs flickering? That's like internal discharge. Alright, focus again on this target. They both illuminate, which is interesting. Let me, let's see. Let's see if I can't get the cover off the relay and we can have a look on the inside. This is a, nobody's heard of them relay brand, Tongling. Basically, they assemble the entire relay and then plop the case on top of it as a last step. The only reason it won't come off is because there's clips under here which are pressed against that the terminal block. Alright, so it's also possible this is shorting internally. One thing you can note right now is that's the entire isolation distance between the two switched elements, so it's obviously not going to be able to, you know, you could probably arc across that with a couple kilovolts. So the relay is obviously not going to be good for that much voltage. Let's see, where did the lid go? The lid claims 10 amps, 250 volts, 15 amps, 125 volts, 10 amp, 250 volts. So it claims the same thing twice. Yeah, so that's your entire actuation right there. So your current for this, obviously one of your pins is right here, so the current runs up through this brass or copper element through here to the pad, and then this goes over to the pin here, this goes to that pin, and then the other side goes to the other one, and obviously it's biased up towards this top pin, which means this is going to be NC, which we can confirm just by looking there. And the relay actuating, the entire movement of the device is just anyways, let's see if we can't see anything more interesting with the lid off. I wonder how many people are just watching this waiting to see how long it takes me to shock the crap out of myself. We are connected. I can't tell where the actual failure is. Let me add a very small amount of light. But you can definitely see the LEDs flashing as it fails. Let's see if I can't just totally destroy the relay. So, alright. Scuff the board a bit, but it shouldn't affect anything too negatively. So there's our relay footprint. You can see the scraping was mine, but there's this pore here where it comes right to there. So I'm assuming the arc path is probably here to here. Let's see if the test behavior changes now that I've thoroughly savaged it. It did, so it went to a higher voltage, which implies that it was arcing inside the relay. It changed. I don't know if you saw it. It's now arcing on the bottom side of the board. So if I take the board and turn it over, we should now see it arc. Yep. So that was interesting. It appeared it actually arced across the isolation gap. Let's see if we can replicate that. Yep. So it's arcing right across the isolation gap. So I guess that tells us this is actually a pretty good illustration of board design stuff, where effectively what I'm learning is that this isolation gap here is good for approximately 5.6 kilovolts. So anyways, I hope you found that interesting. That's a little evaluating high voltage board stuff, high voltage PCB design. I wouldn't have expected this to fail at that low of a voltage. I would have expected it to track along the surface of the board. But this board is relatively clean, so I guess the air breakdown dominated. Anyways, hope you enjoyed.